Okay. So this is like what you can get like for the this. Any question? Okay, never mind. Okay, this is this face does not exist.com. Okay, you can see this picture was generated by the style GAN. Okay, you can use a lot of faces to train this model, and so that you can generate like a photorealistic image. And you may wonder like, well, isn't this like just a real image? Okay, you can actually reload this page. Where's the? You can actually reload this page, and it will give you different face it generated. It will generate different faces each time. Okay. And I also loaded this, you know, this picture. This is like from this rental does not exist.com. Okay, so not only these pictures are fake, this description is fake too. Okay. Everything you see on this website, okay, is generated. Okay, it's fake information, but you can see that it actually, like, you know, you can try to reload it. Okay, and every time it will give you a totally different picture and description. Okay, even generate this owner. Of course, this owner is also a fake one. Okay, but you can see some fishy situation here. For example, look at this name, Marilyn, right? Marilyn is a female name. This face looks like a male, right? So yeah, I mean, some, you know, tiny detail may not be so good, but still it looks very realistic, right? Okay, and recently there's a news. Okay, a YouTuber. Okay, I think that guy is Xiao Yu, right? Okay. That guy is like he used like some famous female, okay, put their name, their face on some like you know, adult video, like you know, to make some pornography and sell those pornography for profit. Okay, and that technique is also based on GAN. Okay, so you can see that, okay, GAN is a very powerful tool in dealing with images. Okay, in dealing with images. Okay, so autoencoder and the GAN, okay, they are both unsupervised learning. Okay, they both learn dense representations, and they both can be used as generative models. Why do I say they can be used as generative model? Because actually, GAN mostly are used as a generative model, mostly. Okay, but autoencoder has a lot of different applications. Okay, so it could be used as a generative model, but a lot of time in other applications it can be used for other purposes. Okay, so not on autoencoder especially is not necessary be used as a generative model, and they have many similar applications. Okay, however, they work very differently. Okay, autoencoders simply learn to copy their input to their output. Okay, if you look at this description, you will feel like, well, if we want to copy input to output, why do we need to have a network? We just copy the input to the output. I mean, it's so easy, right? Everybody can do that, right? Okay, just make a copy, right? Making copy doesn't need a network to do that, right? Okay, but okay, this task may sound like a trivial task, but we will see that constraining the network in various ways will make it really difficult. So we actually intended, okay, intentionally try to make this copy difficult. By making this copy difficult, okay, we force the network to learn some dense representation of the data. Okay? So, for example, you can limit the size of the latent representations. Okay? So, for example, like say we use 10 neurons as the input. Okay? And then in the middle layer, which is what we call latent representation or coding, let's say we only have 5 neurons. When the input has 10 neurons, of course, I mean, output also has 10 neurons, okay? Because we need to copy the input to the output, right? So input and the output need to have exactly the same neuron. Otherwise, you can never make a copy, right? Okay. So, but the issue is when you make the center part only 5 neurons, then your network need to find a way, because remember this is like we are not using skip connection. Okay, here I mean of course we don't use skip connection. If you use skip connection from the input directly to the output, then everything is solved. Okay, we don't need to worry about the middle part of the network. No, I mean it's a feed-forward neural network. Okay, so when you intentionally for feed-forward neural network, when you intentionally make the middle layer narrow, okay, then the middle layer needs to somehow find a way to store the information from these 10 neurons into 5 neurons, right? And then later it will be able to expand it back to 10 neurons. Okay? So that is what we call dense representation of the data. Okay? So you can limit the size of the latent representation. That's what we meant here. Okay? Or you can add noise to the input and train the network to recover the original input. We call this as denoising autoencoder. Okay? So which can be used to remove the noise or do the imputation. Remember, I mean, last chapter we talked about prediction and imputation. We have 2 different things, different tasks for like time series data. One is the prediction, one is imputation. Okay, imputation can be done by denoising autoencoder. Okay, so these constraints prevent the autoencoder from trivially copy the inputs directly to the output, okay, which forces the autoencoder to learn efficient ways of representing the data. Okay, so in short, the codings are byproduct of the autoencoder learning the identity function under some constraints. Okay, you will see examples. I mean, so that you can understand easier. Okay, as for GAN is very different. GAN are composed of 2 neural networks. Okay, one is called generator. The other one, okay, is called discriminator. Okay, generator tries to generate data. Okay, from fake data. It tries to generate real data. It tries to generate data that looks like real. Okay, it tries to generate fake data from real data. So the fake data look as real as possible. Okay, and discriminator, okay, try to tell real data from fake data. Okay, so it's like one is a bad guy. It try to generate like fake information. The other one, the discriminator serve kind of like a policeman. It try to catch, okay. She try to catch if this data is real or fake. If it's fake, it try to catch it, okay. And so by allowing these two networks competing to each other, okay, you will find the generator is getting better and better at generating realistic data. And the discriminator, at the same time, is getting better and better at telling if this data is real or not. Okay? So at the end, when these two parts are very good, okay, when these two parts are very good, we normally use the generator. As I said, like the GAN is most of the application. GAN is used as a generative model. Okay, so we try to intentionally have these two networks competing each other, so that they both improve. Okay. So this type of learning is called adversarial learning, training competing neural networks. Okay, it's widely considered as one of the most important ideas in recent years. Okay, in 2016, okay, Yang Lechong, okay, said that this adversarial learning, okay, adversarial training, okay, was the most interesting idea in the last 10 years in machine learning. Okay, so this intentionally making two networks competing each other is a very interesting idea. Okay, it's very interesting, and that's the foundation of GAN. Okay, so in this chapter, we will start by exploring in depth how autoencoders work and how to use them for dimensionality reduction, feature extraction, unsupervised pre-training, okay, or as generative models. Okay, and because we are talking about generative model, so we will naturally, okay, start talking about GAN. Okay, so we'll start by building a simple GAN to generate fake images, but we will see that training is often quite difficult. Okay, why is it difficult? Okay, we will discuss the main difficulties. Okay, you will encounter with adversarial training, as well as some of the main techniques to work around these difficulties. Okay, but the second part, okay, about GAN, I'm not sure how much I can talk about. Okay, because we now have probably just 6 hours and 6.5 hours left. Okay, so I will try my best. Okay. So first, let's look at these two series. Okay, 40, 27, 25, 36, 81, 57, 10, 73, 19, 68. This is the first series. The second series is this one. So if you look at these two series, if I ask you, okay, which series is easier to memorize? Huh? First one? Some of you say first one. Some of you say second one, right? Okay. Take a closer look at the second one. Okay. Because the second one is 50, 48, 46, 44, 42, 40, 38, 36, 34, 32, 30, 28, blah blah blah. So basically, it's a very simple arithmetic series, right? Very simple arithmetic series. Okay. So next number is basically the previous number minus 2, right? Starting from 50, ending at 14, right? Okay, even though, okay, so intuitively, okay, if I give you two series, if I don't tell you anything more about that, okay, and I want you to memorize these two series, then the first thing first you will say is like, okay, the shorter series is normally easier to memorize, right? Okay, if you only try to memorize them directly, then the shorter series is obviously easier to memorize, right? But, okay, if you are able to observe certain pattern from a series, then it's going to be totally different, right? For example, like this case, okay, intuitively, the first series is shorter, so it looks like a first series is easier to memorize. Okay, first series is roughly half of the size of second series. Okay, but the second series, once you look closer, you will find that it's a simple arithmetic progression, arithmetic series, and you know, you just need to memorize when to start, the rule, okay, -2, okay, and the end, where to end, these three things. It doesn't matter how long it is, right? It doesn't matter. Okay, so the data, okay, so both are data, okay. I mean, of course, you could consider these two as like a, you know, time series data, okay, but let's not to think about time series. Let's just think about them as just data, okay. So these two data sets, okay, you know, if you have a way to find, if you you know, have a way to find like the pattern inside this data set, then it will help you to memorize, to store this information much more efficiently, right? Okay, so that's like a good example, okay, that tells us, okay, remember I told you like, you know, if you have like 10 inputs, okay, how can you have a 5 input in the middle and still be able to put it back to 10 inputs? Because once you are able to find like certain pattern in those 10 numbers, you may not need that many neurons to store the information, okay? You just need to store some pattern information, okay, as the coding, or what we call dense representation, okay, in the middle, okay? So the relationship between memory, perception, and the pattern matching was famously studied by William Chase and Herbert Simon, okay, in the early 1970s. Okay, they observed expert chess player, okay, here we are talking about like a Western style chess, okay, were able to memorize the positions of all the pieces in a game by looking at the board for just 5 seconds. Okay, so the professional chess player, they just look at the board for 5 seconds, and you can ask them, you can ask any of them to put back the, you know, you know, of course, you mean to put like exactly like a pattern, exactly the same pattern on the chessboard, okay, by memorize. I mean, the professional chess player can memorize the pattern very easily, okay, but there's a catch for that, okay. The pieces were placed in realistic positions from actual games, okay, not when the pieces were placed randomly, okay. The chess play experts, they don't have much better memory than us, okay. They just see chess patterns more easily, okay, because of their experience with the game, okay. Noticing patterns helps them store information efficiently. I'm not a chess expert in person, okay, but I do play Go, Okay, you know Go game, right? Okay. I'm a amateur 1D. Okay. Of course, it's not you know, if you, it's not really a very good ranking. Okay, you can easily find like in the Go club at our school who has they have a lot of experts that can beat me easily. Okay, but even for me, okay, after I play one game, you know, the Go game has around more than 200 steps. 200 steps, okay? But we normally, after we play each game, we need to study the move that, I mean, every move that we play in order to improve our skill, okay? We need to study each step that we play. But, you know, even for, I consider my memory very, very poor, okay? But I can memorize every step, okay? More than 200 steps without any problem, okay? Very easily, okay? It's not because I'm expert, okay? Talking about expert, for example, okay? The professional, okay? You know, there are a lot of Go professional player, right? Like a professional, maybe professional 1D, sorry, not 1D, professional player can go as high as 9D, right? Or they normally call it 9P, okay? But anyway, okay, those professional Go players, they can memorize every game they have played since they officially turned pro. Think about that. Each guy, okay, each professional Go player play at least about maybe not more than 100, but at least like 30, 40 games. And each professional Go player normally has a career for as long as normally 30 years or even 40 years. So let's say each year they play only 20 games, and there are 40 years. Then we are talking about how many? 800 games, right? So they can memorize every single game, every detail of those 800 games easily. Okay, close to 1,000. That's crazy, you know. That's crazy. Okay, so this type of stuff, okay. If they do not memorize all this by pattern, nobody can memorize this many games. Nobody can do that. Okay, so this is like something that tells you, okay, some people are better at observing the pattern. For those professional Go player or professional, well, the chess experts, because they have played this game for their whole life, so they can observe the pattern very easily. But you know, they can memorize that because of the pattern they can observe from the game. It's really not because, okay, they have super memory. No, okay? So if you place the chess at random position, okay, those players, those experts, they are not any better than us, okay? So just like a chess player in the memory experiment, okay, an autoencoder look at the input, convert them to an efficient latent representation, okay, the pattern, and then spit out something that looks very close to the input, okay. So we want to, you know, reconstruct the input, okay. So the output is we call that it's a reconstruction of the input, okay. So the autoencoder, just like a GAN has a generator and a discriminator, right? But the generator and discriminator are two different networks, okay, two separate networks. But the autoencoder is one network, but it can it's composed of two parts. The first part is called encoder or recognition network, okay, which convert the input to a latent representation, okay, and this will be followed by a decoder, okay. Another name is called generative network, okay, which converts the internal representation, this latent internal representation, to the output, okay. So this is an example, okay. So the input, you can see we have three numbers, right? But we feed these three numbers into this dense layer, okay, with two neurons, okay. And then these two neurons, it goes to this output layer, okay, which has three neurons because we want to reconstruct the input, right? So this output will try to output this x1 prime, x2 prime, x3 prime. This x1 prime, x2 prime, and x3 prime will be as close as to the x1, x2, x3 as possible, okay? So in this example, okay, this part is called encoder because we try to encode these three numbers by using only two neurons, okay? And this part is called decoder. We try to decode these two numbers back to three numbers, okay? And this idea is similar to the left-hand side, okay? This is a chess, like the pattern on the chessboard, and the guy, the chess expert, I mean, he only needs 5 seconds. Okay, he can memorize this and as a pattern and reproduce the exactly same thing. Okay, by using the pattern he memorized. Okay. So as we can see, autoencoder typically has the same architecture as a multi-layer perceptron. Okay, because, well, this looks just like a multi-layer perceptron, right? Okay, so except the number of neurons in the output layer must be equal to the number of inputs because we want to reconstruct the input in the output, right? So the output, the neuron in the output layer has to be exactly the same as the number of inputs. Okay, that's obvious. Otherwise, you couldn't do that. Okay, no matter how good your autoencoder is. Okay, so in this example, okay, in this example, okay, there is just one hidden layer, which is composed of 2 neurons. Okay, and one output layer composed of 3 neurons. Okay, and the outputs are often called the reconstruction. Okay, because the autoencoder tries to reconstruct the input, and the cost function contains a reconstruction loss that penalizes the model when the reconstructions are different from the input. Okay, so the output should be as close as to the input as possible. I mean, otherwise, it will penalize. Okay, we are going to use the cost function to penalize this model. Okay. So because the internal representation has a lower dimensionality than the input data, okay, here, the input is 3-dimensional, right? We have 3 numbers. And the internal representation is here. This neuron, each neuron, of course, only store one number, right? Okay, each neuron only store 1 number. So this is 2-dimensional, right? So we want to, somehow compress these 3 numbers into 2 numbers, and then somehow reconstruct those 3 numbers from these 2 numbers back. Okay, so we call such when the middle, the internal representation has lower dimensionality. Okay, when your autoencoder has such a situation, okay, we call that autoencoder to be undercomplete autoencoder. Okay, an undercomplete autoencoder cannot trivially copy the input to the codings, because otherwise, I mean, it's going to lose some information, right? Because the dimension will be smaller, right? So you need to use a smaller dimension to represent the original numbers. So that's something has to be done, right? You have to, the autoencoder has to find some pattern, has to find a lower dimensional representation of the data. Otherwise, it wouldn't be able to do that, right? Because it won't, eventually, it has to reconstruct the input in output, right? So yet, it must find a way to output a copy of its input. So it is forced to learn the most important features in the input data, okay, and drop the unimportant ones, okay? So we can see how to implement a very simple undercomplete autoencoder for dimensionality reduction, okay? So if the autoencoder uses only linear activations and the cost function is the mean square error, okay, then it can be shown that it ends up performing principal component analysis. Okay, PCA is an algorithm that does the dimensionality reduction. Okay, PCA identifies the axis that accounts for the largest amount of variance in the training set. Okay, so for example, in here, the blue dots represent the data point. Okay, so what is the direction that has the largest amount of variance? It's this one, right? Right? Because you can see the data point, scatter apart the most in this dimension, right? So this, we call this dimension, okay, principal component. Okay, principal component, okay? So if PCA finds a 1D representation, it is the solid line, okay, this one-dimensional representation. So what exactly is a solid line? I mean, we will let each of these blue dots to project to this line. Well, the solid line is here, but we are going to see yeah, the solid line is a C1, right? Okay, so if we only use 1D, it's going to be the location of the projection for each point. Okay, each point will be represented by the projection on this line. Okay, because this projection capture the most differences between these points. Okay. So that's the concept, okay? Of course, if you have a two-dimensional representation, so you will find the second axis, okay? The second axis, okay, it's okay, now that's, do not consider the variance of this direction, okay? And if we do not consider variance of this direction, obviously the most different variance for all these points will be this direction, which should be proportional, perpendicular to this. The C2 should be perpendicular to C1. Okay, orthogonal to the first one that accounts for the largest amount of remaining variance. So what is the application of autoencoder? application of autoencoder is has abundant applications. Okay, sorry, not all. The PCA has abundant applications. For example, let's say like if you guys know like the cell phone has a accelerometer, right? Accelerometer, 加速器. Okay, it has like a 3-dimensional accelerometer built in your smartphone. Okay, so but when you mount your smartphone in a car, okay, for example, how does it tell that which direction is like the direction that cars advances? Of course, I mean, when you mount this thing to the car, everybody can mount it at different angle, right? Okay, so but it doesn't matter. Okay, so it will collect like its X, Y, Z component from the 3D accelerometers, and then okay, it will try to use PCA to find the most variance of the accelerations, okay, in your car. What is the largest acceleration in the car? Going straight forward? No. It is the force that keeps us on the ground. Going down, the G force. G force is about 10 meters per second square, right? Okay, nobody can drive their car with such a G force. Okay, I mean, go so fast. Normally, I mean, unless you are driving a racing car. Okay, so basically, okay, when you do the PCA, okay, the largest component you get, okay, that direction is pointing to the ground. Okay, and then okay, the second the second dimension will be the direction that the car advances. Okay, so and then you can use that to tell like okay, I mean the side of the car. Okay, basically you do like the cross product to get the side of the car, the third dimension. Okay, I just want to tell you, okay, the PCA has many important applications, okay, which can be used like in sensor data. Okay, so this type of stuff. Okay, well, we're running out of time. So next week, okay, next time we are going to use autoencoder to do the PCA. So I will show you how to use the autoencoder to accomplish PCA task. Okay, basically it's just like this, exactly just like this. Okay, because we are getting 3-dimensional information, and then we are going to use 2-dimensional to represent that 3-dimensional information. So this 2-dimension will be the 2D information for the PCA. Okay, assuming you are not using you're using linear division only, and the cost function is a mean square root error. Okay. Okay. So yeah, I think we're running out of time. So let's stop it today here. Okay. Any question? If no question, next time we'll start from here. Okay. Basically, hopefully next time we can see if we can finish as much as possible for the autoencoder, and hopefully talk a little bit about the GAN before end of the semester. Okay. Any question? Okay. So I'll see you next week then. Okay. Thank you.